formation of the solar system. So you have heard and seen this figure many a times right now, right? So what I want to say here is that we have to make a model for formation of solar system. In order to do so, you should understand what exists, what is there. And this can be only done by the observation or the laboratory methods. By observation, we know that we have one star, 8 planets, out of which 4 are terrestrial planets, inner planets, and then 4 giant planets, out of which 2 are gaseous, 2 are icy kind of planets. So we have 8 planets. Few planets have moon around it, and if you calculate the total number of moons that have been detected till date, is around 293 moons. You can also call them satellite, because we say moon for our Earth satellite is known as moon. But a general term, moon means the satellite around the planet. So there are around 293 moons of satellites that have been detected till date. There are 5 dwarf planets. You have heard what are dwarf planets from Debabrata. And the asteroids that is a belt between Mars and Jupiter. You can see here dotted lines are around 1.3 billion asteroids. And the comets that come from the outer region of the solar system is around 3,900 known comets till date. Okay, so there are many objects in the solar system. So if you really want to study them and come to a conclusion of formation of solar system, it is pretty immense work. Yeah. So any theory to describe the formation of our solar system must be consistent with the observable facts. So other than this, we need to know all the first observation facts, and then we'll come to the laboratory analysis facts. And I'll try to modify the formation of solar system with you and see which one suits better. Yeah. So the first challenge is the pattern of motion. You know this already, but let me go through it still. All planets orbit around the sun in the same direction, which is counterclockwise as seen from the Earth's north pole. Planets' orbits are nearly circular and they are coplanar. Planets rotate in the same direction which they orbit. Almost all moons orbit their planets in the direction of the planet rotation. And last, the sun rotates in the direction planets orbit. So you know that everything seems to be similar, going similarly. This is the first challenge you have to explain. The second challenge was to explain between these two distinct group of planets that I showed you just in first slide. So that they have the first 4 planets are known as terrestrial planets because they have a solid surface, and these are very close to the moon. They have small masses or radii. They are very rocky, solid surface. The density, therefore, is very high. Their rotation is very slow. They have a weak magnetic field, as Debabrata was showing. And they don't have rings like outer planets, and they have very few moons. Now, compare this to the Jovian planets. Jovian planets are the outer planets like Jupiter, Saturn, Uranus, and Neptune. These are far from Sun, large mass, large radius. They have gaseous surface. They are low in density. Their rotation is very fast, and they have strong magnetic field compared to the terrestrial planets. They have many rings, especially Saturn, if you know, and they have lots of moons. Yeah, hundreds of moons in Saturn itself. Yeah. So the question for the second challenge is, why is the inner part so different from the outer part? There is a distinct difference between the two. I mean, the observer that you can observe very easily. Yeah? The third challenge is to explain the asteroid belt and the comets that come from far off. Yeah. So the asteroids are small rocky bodies that orbit the sun, mostly between Mars and Jupiter. As I show, it's called an asteroid belt. There's a classification to asteroid belt too, which I'm not discussing today. But as I said, there are 1.3 million asteroids that have been discovered. As of comets, they are small and icy body that have spent most of its time beyond the orbit of Pluto. So, as I said, 3900 comets have been discovered. And actually, comets occupy 2 regions. One is Kuiper Belt region and one is Oort cloud. I didn't talk about Oort cloud this time, There may be something else, but you have to know that there are two regions of comets from where the icy body comes. So from this, we know there is an existence and there is a property of these small bodies too. They are large in number, but they have their distinct properties. Yeah, this is asteroid is more like terrestrial thing, and comet is more like outer material, right? So now the fourth challenge that is exception to the rules, yeah, which don't follow the rules I talked about, yeah. So like Mercury has a large eccentricity, orbital eccentricity, or Uranus is very tilted, yeah, in rotational axis, or Venus rotates backward. It is clockwise. Everything rotates counterclockwise. This is clockwise, yeah. And Earth has a large moon comparatively to other moons that you see, so that these are some of them. There might be many exceptions which you would like to put in, but as of now, let's go with this. Yeah. So the least that a theory should deliver is convincing explanation to the gross features first. The small features probably you can still explain later on. First, the gross things should be we should be able to explain for any model of formation. So since 17th century, people have given various models. I think there are around 10 to 12 different model of formation of solar system. So if you go to Google and check various model hypothesis of solar system formation, you'll find immense number of them. Yeah. But let me just put forward two or three just for the sake of the feeling that there were many things that were going on from 17th century to say till now 21st century. We are still fiddling with the formation of solar system, right? Still we have not come to a conclusion of a real good model for solar system formation. Yeah, so let's see if you find this very interesting. So first one is Laplace nebula theory. This was given earlier in 1750 and it has continued. It has been, this is the one theory, nebular theory, which has been taken till date. Yeah, but so it started with it says that there is a cloud kind of a system and this becomes oblate because of the rotation and flattens, and then there is a star and the planets form together. Yeah. So the problem with this kind of system was that the differential rotation between the inner and outer parts of the rings would prevent the material from condensing. The planets wouldn't form the kind of system they had given. This is not a detailed version. I would expect you to read a detailed version if you really want to know about this. So another one was tidal theory, that the sun was already there and a star passing by. Due to the pull of the star, the material from the sun made a filament kind of a structure, and this filament is forms the protoplanets and planets eventually. So this has its own kind of every model that was given has its own kind of problems associated with them. The most important problem associated with this was, so if you do a theoretical modeling to this, I mean, there are many. First is that sun and planets give the same age, whereas here it is not. And second is that you cannot make anything beyond 4 solar radii, which is like within Mars orbit, you need to form all the planets. Yeah, if this is the condition, tidal theory. So these didn't work out. Another theory which I found very interesting was that there's a sun and then there's a star going by, and the protostar's material is captured by the sun. Instead of star capturing sun's material, this is other way around, and it makes a circle around the sun. Again, you cannot explain. You will need millions of such protostars to move around sun to capture the amount of material that we see as of today around sun. So again, this was not, and there are many more. Yeah, you can check this out. Now, the other parameter that I would like to include when I'm talking about formation of solar system is that you analyze some samples in lab and see the isotopic and elemental workings, or do a chronological measurement of these to understand when it was forming, so that you can give a very concise and a better solar system model. So many samples have been measured. I hope you know meteoroids come from mainly from the asteroid belt. So two asteroids hit each other. due to a resonance created by Jupiter in general. And these, when they hit, a material from asteroid comes out. And when they enter the interstellar medium, they are called meteoroids. When they come into the Earth's atmosphere, it's called meteors. And when it falls on the Earth, it's called meteorites. So these meteorites, we collect these meteorites and measure in lab. We have meteorites, around 4,000 meteorites that have been collected worldwide, and there are also some from Moon as well as Mars. So we have free samples from Moon and Mars. We didn't have to send space shuttles or spacecraft to get these from Mars and Earth. So we are lucky. Meteorites are in general called poor man's space probe actually, because you get it for free. So we have free samples. And also there are some interplanetary dust material that come from comet and asteroids, ablated asteroids. So if you have a low flying aircraft, you can catch this interplanetary dust particles in the stratosphere level. So if you go some 30, beyond 35 kilometers of our Earth's surface, you can catch them and bring it back to lab. So it's an easy way of getting comet samples or asteroid samples. And there are also micrometeoroids. When the ablated meteoroid fall into the system, because of the flash heating, they form like spherules, small spherules, and they become like a micro meteoroids and fall on Earth. So if you collect them from different regions, from deep sea sediments, or from the Antarctica snow, or from the deserts, you get these meteoroids and micrometeoroids. You might find some of. So in lab, back in lab, I have just put three because I mean, I didn't want to overwhelm you, but there are n number of instruments that you can use to analyze these materials. You can analyze them for water, organics, element morphology, elements, and see what kind of material was there. So this is something which we are talking on basis of meteoroids. So I just want to, what Devavrat Banerjee, when he was giving a talk, I just put this slide so as to just give you a glimpse. So these whatever I'm showing is first forming solids from the asteroid, from the meteoroid basically. So what you do is take the meteoroid, cut a section, and look at it with a naked eye. So if by a naked eye you will see a amoeba kind of a structure, it's very whitish. This is the first forming solid, which is calcium aluminum inclusion. Yeah. So how do I know it's first forming? You need to date it, right? So you will date this and say if it is first forming solid or not. And this will tell you when the solar system formed, because it's first from the condensation sequence, what mineral will form when. You can calculate it. There's a thermodynamical calculation, and you can say that this can form first or second or third. Yeah. Similarly, there's another object which is called chronology. They just follow this calcium aluminum inclusions. They form later, within a million years. They form from dating. We know that they form from 1 to 2 million after CI formation. So what people have done in lab, they have measured the CI's chronology by uranium lead dating. When you say uranium lead dating, it is a long radioisotopes, and you measure this to get the absolute dating. I mean, it's one absolute dating you get from it. But when you do aluminum magnesium, it's short-lived radionuclide, like what Devavrat was talking about. This is a relative chronometer. Means I will take a CI, I will measure that first one, and then I will do a relative dating of rest of the CIs depending on the first solid formula. Okay, so relative dating. This doesn't give an absolute dating because we are not sure what was the initial composition of aluminum magnesium. I hope it will be more clearer when I go through few more slides. So as an example for this, I'm not sure how much you know about isotopes, but let me still go through this. There is an aluminum magnesium systematics. For aluminum, it's a monoisotope, stable isotope, 27 aluminum. 26 aluminum is radioactive. It will decay into 26 magnesium with a half-life of around 0.73 million years. Okay. 24, 25, 26 magnesium are stable isotopes, and they have a particular ratio of 25 by 24 or 26 by 24 in our solar system, which is pretty homogeneous. Now, if I have 26 aluminum in say CI, which I was talking about, and this 26 aluminum decays in situ, in there, it doesn't communicate with the rest of the material, just within CI it decays. What will happen is there will be an excess of 26 magnesium. This is what we measure. So we measure this excess of 26 magnesium, and then we say that 26 aluminum was present in the CI, and then we date it back. So for dating back, if you are a nuclear physics student, you will know there is a famous radioactive equation, which is N is equal to N0 e raised to minus lambda T. So half-life, I have told you, the initial composition by present composition by initial composition is what you will measure with the half-life. Yeah, and this will give the chronological parameters. So now I have something observable that I see is systematically there. And now I have a chronological parameter of various bodies that are formed that I have in hand. Yeah. So I know this. So putting this 1:1 together, I will try to do much better modeling. Yeah. Okay. So not only this, we have more to add to it. Now, when you're making a model, you need to know the initial composition of the molecular cloud, yeah, from which the solar system will form. So if you look back at the nebula model which I was talking about, it was there was a cloud and there was protostar and there is an orbit of planets that form eventually. But this molecular cloud is not really single molecular cloud. It comes within a giant molecular cloud. So giant molecular cloud is something which has one hydrogen per centimeter square. It has few denser molecular cloud within it, which is like 10 raised to 3 hydrogen per centimeter square. And there are cores. The cores are the one which basically gravitationally collapse to form a star or a planetary system. So some cores will form star and some will form planetary system. That's it. It's statistical. Yeah. Now now so you know that our molecular cloud from which we have solar system has formed is surrounded by various stars because there were many cores surrounding it. So for example, I don't know how much you know about the stars, but let me still name it. Suppose we had a supernova nearby or a asymptotic general somewhere nearby. These are they they are nucleosynthesizing new material in themselves, nucleosynthesizing material within themselves, and there is death of star. When there is a death of star, they throw away the material outside. So any material between two star, any space that between two star is called interstellar medium. Yeah. So this interstellar medium is very vacant kind of a system where the material that has been thrown away by a star, a dead star, comes into interstellar medium, and this interstellar medium becomes a part of the molecular cloud. So the composition of our molecular cloud depends on the stars surrounding it. Not only that, there are some circumstellar grains that are formed around the stars that will also fall in our molecular cloud. So not only we can analyze this and tell what was the composition, which stars were basically contributing to our by analyzing elemental and isotopic composition of these grains. Also, there are organics forming in interstellar medium that also comes along with this pre-solar grains. Most of the pre-solar grains, not most, but 50% or 60% of the pre-solar grains are coated with organics when they come into the system. So one of the question always remains whether the life has come from outside, from the interstellar medium through pre-solar grains. So this has been a question, yeah. So now I say that there are stars, there are pre-solar or circumstellar grains coming along with organics, along with other material like short-lived radionuclides or other radionuclides and elements into a molecular cloud, which decides the initial composition of the system. Not only this, you can calculate basically whether the molecular cloud was collapsing self-gravity, within the self-gravity, or was it a triggered collapse? So for a triggered collapse, you need to find out an isotope that is formed in, say, supernova. And suppose supernova is triggering it. So the timeline should be of the isotope should be such that it can talk about the time scales from when the star died to the first formation of solid in the solar system, which has been done in PRL in itself. We have done 41 calcium isotopes to say that probably it's a triggered collapse and the triggering is from the supernova. So there is much of work involved in this, but that's one of the best papers, which is communicated from PRL, which talks about triggered collapse from short-lived radionuclide. Now here I have also shown various pre-solar grains. You can see the size of the grains. They are very, very small. They are micron size, 1 to 5. 5. When I say 5, it's the largest size probably. Probably they are very small grains, less than a micron. They are in nanometer scales. So when you have to analyze such kind of grains, you need to have a very sophisticated instruments. So that's what Praveen was introducing Vikram, saying that he has one of the sophisticated instruments. So PRL also deals with very sophisticated instruments and works on these kind of grains. So now coming back to formation of solar system, which is topic of my talk. So we'll come back to the nebula model. Now, this has been evolved with time till now, and I will make some changes, but let me give you a fair view of this system, which is shown here in different parts and passes. Okay. So first, a cloud of interstellar gas and dust is called solar nebula. Most of it is 98% hydrogen and helium, but it includes atom and dust grains of heavier material from the previous generation of stars. I talked about this, yeah. So now this starts, this becomes thick and either gravitationally collapses or there is a triggered collapse to form the sun at the center. So there is a dense material in the center, and this becomes denser and denser by collecting the material from inside. So a star will form when hydrogen fuses to helium, and this has to form at the center. Okay, but the rest of the material rotating along with the star becomes a flattened disk kind of a structure due to the angular momentum, and this rotates along with the star when the star is still in the forming condition. It's called protostar, yeah, proto sun, you can say proto sun, yeah. Now, yeah. So the contraction leads to protosun in the center, and there is an accretion disk, and there is heat which vaporizes the dust. So more or less, this becomes a homogeneous disk or homogeneous nebula in some ways, if you see. Yeah. Now after this, where the grains are very nearby, the grains start sticking to each other. There's no other way you can make a body from dust. So the dust starts sticking to it. It's called coagulation kind of. By sticking, it makes a bigger object depending on how much material is around it. When it becomes a planetesimal kind of a structure, you can say when it can gravitationally attract. So gravitational works only after certain mass. So it will gravitationally attract material from the side by and become a bigger planetesimals. So planetesimals means a stage before formation of planets. Yeah. So this is the time where small asteroids or something are forming. Yeah. And finally, these planetesimals evolve to planets in billions of years. In 100 billion years, probably the evolution of planets have taken. In fact, there are differentiation processes that has also taken place. During this, there's a lot of impact going on. So the planets are being hit by the other objects which haven't been formed, yeah, like from the asteroid belt. So dynamically, it's a very active state, but the star has started uh, uh, basically started the nuclear reactions. So hydrogen and hydrogen is burning to helium and radiation has started. Yeah, this is the point where we say solar system has formed 100 million years and everything is formed, right? So till 2020s, we are thinking the solar nebula formation scenario is one of the best scenario. This is the best scenario that you can see for the, and it's most widely accepted model. Yeah. But then what happened is that we had a sample return mission. So one of the first sample return mission was the from the Will 2 comet. Yeah. So this was in 2006. The sample was brought down. This is a NASA. This is NASA's mission, and Will 2 comet samples were brought back in something like this is a brick of aerosol. It is a very light material, and you can see tracks in between. These are the small grains that have been embedded in aerosol. So we remove these grains from the these, and then we analyze these in sophisticated instruments. Now, what happened was the idea that the comets form in outer regions. I did talk about this, yeah, that all comets form in orbits beyond Pluto. But the material that we saw were not like this. It was the material more like CIs, calcium aluminum inclusion, that forms pretty close to the proto-sun, basically. So from this sample determination, the idea of inner material being mixed with the outer region, which is at 40 AU. It's a long distance, yeah. So there is a long distance. So there has to be a model which states that there are solar winds, which are called X winds, which carry this mineral and throw the material in the outer region, which is far, far away from the sun, yeah. And there is a churning, basically, of the first solids or the inner material with the outer material till the planetesimals or embryo of solar system have formed. Till then, when it is in dust sequence or first forming solids are forming. Okay, so other than this, this changed the model scenario of origin of solar system, and then apart from this came the new results of exoplanets. You have heard about exoplanets. In 2013, I think first exoplanet was reported. Now, if you have heard about exoplanets, you might have heard that they have majorly seen planets of Jupiter size, and they are very close to the sun. That's why they're called hot Jupiters, hot or warm Jupiters. So if you look at one of the system, exoplanetary system like Kepler 11 system, you will see that there are planets, there are many planets. It's a multi-planetary system. But all the planets revolve around the sun within the Mercury orbit. You see that? That it's within the Mercury orbit. So what is happening here? Our solar system is unique, or the exoplanetary system that we are looking at unique. So again, there was modeling parameters that were taken care of, and people started thinking again last decade. And since then, they decided there's a new model which was revoked, is of migration of planets. What is migration of planets? There was a theory, Nice model, and there is a second model which is called Grand Tech model. Yes, so Nice model and Grand Tech model are similar. They talk about migration of planets. So what is happening? Let's come back to the embryo stage again. So when the sun is in proto-sun state, first planet to start forming is Jupiter. Okay, Jupiter has a core, and which is like 10 Earth mass or something of that sort. Okay, now Saturn is in a smaller embryo region, and even further small embryo is of Uranus and Neptune. But the Jupiter is being pulled by the sun's gravitation. So Jupiter is pulled, Saturn is pulled, everything is being pulled by the sun. But at a certain moment, when it moves from 3.5 AU, AU is the astronomical unit, from where the Jupiter has formed, it is moved from 3.5 AU to 1.5 AU, where Earth has formed, yeah? Where Earth is right now, around 1 AU. Till there it comes, and then there is a resonance catching between the Jupiter and the Saturn. It's 3:2 Jupiter resonance, it's called. What is 3:2 resonance is when Jupiter takes 3 revolution around the sun, this Saturn will take 2, and they get logged. When they get logged, they have in this stage they cannot move further because there is more mass. together moving inside. And till then, the outer region has been swept by this migration. So the total outer material has a torque, and inner material has a torque. Outer material torque is lesser than the inner material. So the Jupiter and Saturn start moving backwards. Okay, because of this. So the migration is going inside towards the sun till 1.5 AU, then going back to the original position where Jupiter is as of today, which is around 5.2 AU. And then finally, by when it's moving, it's also collecting all the material around it. That's why Jupiter is very, very big. Yeah. And it is said that because of the Jupiter's gravitation, there should have been a planet where the asteroid belt is. So the planet couldn't be formed because of the gravitation of Jupiter, and you have small pieces that are thousands of kilometers there and billions of pieces there. So the migration theory is something new that has been added to understand the formation of solar system, that it evolved this way, and these are the few steps, like the mixing of material before this, and then the migration of planets, and to see what we see as of today in the solar system. So with this, I would say I have finished, and